In a video game that we are making for an Italian customer, the player controls a dragon which must collect the selected lanterns. Since the lanterns are positioned randomly in the space, the animation does not have to be fixed. It should be different based on where the lantern is located. Today, we'll recreate the dragon's movement in Unity. To create the dragon's movement, we had two possibilities: use a standard or a procedural animation. Since the movement of the dragon is different every time and dependent on the selected lantern, we decide to follow the second choice. To do this, we use inverse kinematics. Specifically, we use a simplified version of the fabric algorithm. But first, what is inverse kinematics? We are used to think of an animation in a simpler and more linear way. This is called forward kinematics. Thinking about our robotic arm, for example, having the length of its segment, we can rotate its joint and easily calculate the arm's end position. Inverse kinematics solve the opposite problem. Having an origin point and a goal, how can I position and rotate the segment of the arm to reach it? There are many ways to calculate this. One of these is the fabric algorithm. Fabric stands for Forward and Backward Reach Inverse Kinematics. The concept is quite simple. Let's start by dividing two cases. The goal is too far to be reached, and the goal is reachable. In the first case, we should simply extend our arm toward the target, which is rather easy to calculate. In the second, instead, we should proceed like this. Backward phase. The last point of the arm is positioned on the target. The previous point is calculated by drawing a line between them and keeping the distance they previously had. And so on until the root. At the end of this phase, the root has been moved. So the forward phase is necessary to impose the root at the origin point. In fact, the forward phase allows us to respect the constraints. The root is positioned at the starting point. The next point is calculated by drawing a line to the point calculating the backward phase and keep the correct distance, so on until the leaf. By iterating these phases, an ever better degree of precision is achieved. The iteration continues to the maximum number of iterations or until the distance between the leaf and the goal is sufficiently small. This algorithm is in fact heuristic. It allows to approximate the arrival point based on the tolerance and the number of the maximum iterations. Having to move the dragon, we can easily simplify this. Let's put ourselves in a condition that the target we want to achieve is the dragon's head. It is always reachable from the body, so we can avoid the first check. Furthermore, it is the head that drags and moves the rest of the body, so we must not impose the constraint that the tail is locked at the origin. In other words, the backward phase is enough. Not having a forward phase, even the iterations aren't necessary. We will always be sufficiently precise at the first iteration. We have just to calculate the position and the rotation of all the dragon bones. Once the dragon's body is animated, we must take care of the head. It has to find the right way to the selected lantern and not bump into an obstacle. To do that, we turned the dragon toward the target and gave a viewing angle in which we made raycast, at certain distance. We decreased the number of raycasts by placing an interval, considering a thickness for the dragon's body. If one of the raycasts meets the target directly, the dragon chooses this as the direct path. Otherwise, if it encounters an obstacle, discard the direction. If it encounters nothing, no obstacle, it lists the direction as possible. At the end, it chooses the direction in the middle of all the possible ones. Once the logic was completed, we rigged the dragon and created the texture. Then we positioned the legs to give them a pose suitable for flight. Without a needle animation, we place a fake target in the sky that the dragon chases if there are no other active targets. By clicking on a target, this becomes the active one. To allow a more comfortable search, we have allowed the user to rotate the camera when holding down the right mouse button. Finally, we have positioned the colliders and decorated the scene with models downloaded from Sketchfab and Google Poly, link in the description. After adding the particles and some post-process, this is the final effect. Let us know what you think about this project, it's available on GitHub. Would you like to see a video on a more complex animation and going deeper on Fabric implementation? Let us know in a comment below. This week we opened our Discord server, to allow the people of the community to help each other and exchange ideas. You are all invited. See you next time. Cheers!